What specific problem does the Navigation World Model, NWM, aim to solve in the context of robotic navigation, and how does this problem relate to the limitations of existing state-of-the-art methods?
The Navigation World Model, NWM, aims to address the limitations of current state-of-the-art robotic navigation methods, which are primarily hard-coded and unable to adapt to new constraints after training, such as avoiding specific turns. Additionally, existing supervised visual navigation models lack the ability to dynamically allocate computational resources to tackle complex navigation challenges. NWM seeks to overcome these issues by simulating potential navigation trajectories based on past observations and actions, allowing for flexible planning in both known and unknown environments. By leveraging a conditional diffusion transformer, CDIT, NWM can efficiently scale and learn from diverse navigation data, enhancing its predictive capabilities and enabling it to generate novel navigation plans. This approach not only improves the adaptability of navigation policies, but also enhances performance in environments that were not part of the training dataset.
How does the proposed conditional diffusion transformer, CDIT, work? Illustrate the methodology step by step, detailing any novel components introduced in the process.
The conditional diffusion transformer, CDIT, operates as a temporally autoregressive model designed to predict future states based on past observations and actions. First, it utilizes a cross-attention mechanism where each query token from the current target frame attends to tokens from past frames, contextualizing the representations through a skip connection layer. Second, it incorporates continuous action conditioning by mapping translation, rotation, and time shift actions to sine-cosine features, which are then processed through a multi-layer perceptron (MLP) to create a conditioning vector. This vector is combined with the outputs of the attention layers, using an Eta-LN block to generate scale and shift coefficients that modulate the layer normalization outputs. Finally, CDIT's architecture is optimized for efficiency, as its complexity is linear with respect to the context length, allowing it to handle longer sequences effectively, while requiring significantly fewer floating-point operations compared to standard diffusion transformers.
Can you provide a concrete example demonstrating the inner workings of the Navigation World Model, NWM, and the planning process, perhaps using the forward-first trajectory planning as an example?
The Navigation World Model, NWM, operates by receiving the current state of the environment, represented as an image, along with a navigation action that specifies movement direction and rotation. For instance, in the forward-first trajectory planning example, the agent is constrained to move forward for 5 steps before making any turns. During this process, NWM simulates the trajectory by predicting the next state based on the current state and the specified actions, effectively rolling out the navigation plan. The planning is optimized using the cross-entropy method, which minimizes the perceptual similarity, measured by LPIPS, between the predicted final image and the goal image. This approach allows NWM to effectively navigate while adhering to the specified constraints, demonstrating its capability to plan trajectories in a structured manner.
What are the theoretical benefits of using the NWM for navigation tasks compared to previously established methods like Nomad or Diamond?
The Navigation World Model, NWM, offers several theoretical benefits over established methods like Nomad and Diamond. Firstly, NWM utilizes a conditional diffusion transformer, CDIT, that scales efficiently with model size and data, achieving better future prediction results while requiring significantly fewer computational resources, 9 fewer flops, compared to standard diffusion models. Secondly, NWM is trained on a diverse range of environments and embodiments, allowing it to generalize better and adapt to unknown environments, as evidenced by improved video prediction and generation performance when trained on in-labeled data from Ego4D. Additionally, NWM can simulate navigation trajectories and incorporate constraints dynamically, enabling more flexible planning compared to the hard-coded policies of Nomad. Finally, NWM achieves competitive standalone performance and state-of-the-art results when combined with existing navigation policies, demonstrating its effectiveness in goal-conditioned navigation tasks.
How was the Navigation World Model, NWM, validated? Describe the experimental design, datasets used, key metrics for performance, and how these findings support the effectiveness of the model.
The Navigation World Model, NWM, was validated through a series of experiments that assessed its performance in both known and unknown environments. The experimental design involved training on diverse datasets, including scanned Tartan Drive, Recon, and Huron, which provided video footage and navigation actions, as well as labeled Ego4D videos for additional context. Key performance metrics included absolute trajectory error, 8, for accuracy, relative pose error, RPE, for pose consistency, and perceptual similarity measures like LPIPS and DreamSim. The findings indicated that NWM achieved competitive results in standalone planning and outperformed existing navigation policies when used to rank trajectories, demonstrating its effectiveness in generating accurate navigation paths. Additionally, training on in-labeled data significantly improved video predictions, further supporting the model's robustness in unfamiliar environments.
What specific results were achieved with the NWM in comparison to other methods, particularly relating to navigation performance and accuracy on the different datasets mentioned in the paper?
The Navigation World Model, NWM, achieved competitive standalone performance and state-of-the-art results when combined with existing navigation methods, particularly Nomad. In the experiments, NWM was evaluated using absolute trajectory error, 8, and relative pose error, RPE metrics, demonstrating superior navigation performance across various datasets, including scanned Tartan Drive, Recon, and Huron. Additionally, when ranking trajectories sampled from Nomad, NWM yielded state-of-the-art navigation performance, with more sampled trajectories leading to better results. The model also showed significant improvements in video prediction and generation quality when trained on in-labeled data from Ego4D, enhancing its ability to generalize to unknown environments like the Go-Stanford dataset. Overall, NWM's integration of planning with constraints and its ability to leverage diverse training data contributed to its enhanced navigation accuracy and effectiveness compared to previous approaches.